Okay, so this is section 2.4, sort of the first new material that we're going to see in this course. Although we did do a little bit more fancy algebraic manipulations, it still would have been fair game for a grade 10 math student to do. We're now sitting in a situation where we're going to start looking at the real true reason why we did all this work, other than just getting prepared for the beginning of the year. And that is, of course, simplifying rational expressions. Okay? Now, what is a rational expression? Well, the word rational actually comes from rational numbers, and rational expressions and rational numbers are the same thing. In fact, all rational numbers are rational expressions, but rational numbers are what we are used to. Rational numbers are the set of all numbers that can be written as a over b, such that a and b are integers, and b can't be 0. In other words, fractions. Okay, and there are some rules that we know for fractions. There's rules for adding, subtracting, multiplying, and dividing. We're going to be using those rules, okay, similarly, but of course we're going to be doing it in a more complicated fashion algebraically. So rational numbers, again, are a result of a division operation. So we basically did factoring, which is kind of division, but now we're going to be doing some division processes that don't divide equally. So we're going to have denominators, and those denominators will probably remain. And as a result, we're going to get to as simple as we can and then go from there. There's a couple of considerations that are going to be really important about fractions or about rational numbers that we need to keep in mind. One of them is, and again, there's a whole set of rules and conventions, so we will be going over those, and we will be comparing them to our rational expressions. And we're going to be adding, subtracting, multiplying, and dividing rational expressions. But of specific importance in general, as well as important specifically to this lesson, our fractions are best compared in reduced or lowest terms forms. All of our answers should be in lowest terms. So that's one key feature we need to keep in mind. The second feature that we need to keep in mind for today is not just reducing fractions, which is going to be the focal point of the simplifying, actually, but it's also something about the denominator. The denominator of a fraction cannot equal 0. Unless you're Chuck Norris, you cannot divide by 0. So keep that idea in mind. Okay, that's something that's going to introduce some situations. If you have a fraction of 4 over 5, obviously the bottom's not 0, but you did have examples when you did a slope calculation in grade 9 and grade 10. If you got a slope of, like 1 minus 3 all over 4 minus 4, right? And you get a result of, well, a negative 2, but the big issue is the 0 on the bottom. Can't have that. That's undefined. That's a vertical line, okay, or a slope that's either visualized as infinite or visualized as undefined. There is no run to go along with the rise. This is the situation that we need to worry about. So a rational expression, how is that different than a rational number? It's not. It's the same thing. However, rational expressions include fractions with number portions in the numerator and denominator, but are also algebraic expressions. That's where the rational expression name comes from. Okay? Rational expressions generally are referred to as a result of the division, okay, of at least one expression by another expression that does not divide out completely. So when we factor, we divide, but we usually factor so that we can divide everything out and we have nothing in the denominator. In this case, there's something left in the denominator. So these are all rational numbers: 2 over 3, or 2 divided by 3, negative 2 divided by 3, 0 divided by 3. All of these are legal, and you can have a 0 in a numerator, but you can't have a 0 in the denominator. Rational expressions are all of these guys. See, I have the number 2 over 3 in there. But it could be 2 over x or x over 2. So we have a variable in the denominator. We have a variable in the numerator. Here we have a variable in both the numerator and the denominator. And here we have a more fancy or a more complicated quadratic or trinomial in the numerator and trinomial in the denominator. So to start with, analyzing any quotient, which is really what a rational expression is. A quotient is the result of division, and that's what a rational expression is, the result of division of two quantities. We need to make the following considerations. Are there any values of x or y or any other variable that are not allowed? Key to remember, what's not allowed about a fraction or a rational number or a rational expression? You cannot have a denominator equal to 0. Okay? Second consideration is the expression in lowest terms so that we can compare things and do any other things that we may want to do. So is it the least value of the numerator and denominator while still maintaining the proportion or division result that exists between the numerator and the denominator? So let's look at the following rational expression and we'll learn from the examples. Okay, so consider the following rational expression. In here, are there any values of x that are not allowed? So there's my rational expression there. It's got a 4x squared in the numerator. It's got a 2x in the denominator. Are there any values of x that are not allowed? Now remember, we can have anything in the top, in the numerator. Okay, but the denominator are special considerations. The special considerations are that this guy in the end cannot equal 0. And we even write that as not equal to 0. Okay, so if 2x cannot equal 0, what value of x can there be that is not allowed? Well, you may try some values, like x is 1. That's cool. 2 times 1 is 2. That's not 0. Nice. Okay, what about 2 times -1? Still negative numbers. -10, +10. Try them all out. All of them are not 0. However, if I put in a 0 for x, 2 times 0 is 0. We can't have that value because we can't have a denominator that equals 0. That's not allowed to happen. So here, these values that we're thinking of in the variable x's in this expression are not really governed by the numerator. The numerator we don't even look at to see what's allowed and what's not allowed. But what we do focus on is what x values cannot be in this case. Okay, and sometimes it's an easy way to find out what you can have is to find out what you can't have, and then everything else is cool. All right, we call these restrictions on the denominator or restrictions on the value of x, and in this case, x cannot equal 0. The second question is the expression in lowest terms? Okay, so if I look at that expression 4x squared over 2x, is that in lowest terms? Well, I think if we look at it, even without some experience, we can see, well, we know the 4 over 2 for sure can divide out, can't it? Okay, and remember that this is 4, basically 4 times x in the top, or in the numerator. And the denominator, it's 2 times x. So 4 divided by 2, leaving us with a 2 in the denominator, we're left with a 2. Or, quite frankly, just a 4 divided by 2. Numbers affect numbers. X divided by x, that guy cancels out, doesn't it? Which leaves us just with this solitary x in the numerator and nothing in the denominator. So in this case, to write it in lowest terms is not 4x over 2x, it's just 2x over, or 2x over 1, really. Because there's nothing left in the denominator. Everything is canceled out. So that division is actually a complete division that occurs there. Okay, so that would be it in its lowest terms. Okay, so when we look at it, is the expression in lowest terms, if not simplified by dividing, what we end up understanding is 4x squared over 2x is actually equal to, excuse my form because I shouldn't be going across here, but it's actually equal to just 2x. As long as x cannot equal 0. That's one value I can't have. And you may say to yourself, yeah, but sir, if it cancels out, okay, here you can't have a 0, but if this is the same thing, then you can have a 0 in here. 2 times 0 is 0. That's cool. There's no rules on what numerators can be. However, it does introduce a complication, and that complication has to do with when I have values for this that cancel out, it actually creates a hole in the equation. So that x is equal to 0, if I was to graph this equation, okay, if I was to graph the equation 2x, which is y is equal to 2x, if that's an equation, and there's my y-axis and my x-axis. What actually ends up happening is 2x starts with a y-intercept of 0, because there's my y-intercept there. It's got a slope, a rise and run of 2, okay, and another rise and run of 2, okay, and so there's my line. You don't just connect the dots like you normally would do in this one. Okay, what you would do is you would put a hole in the center there, and I guess you'd have to erase that value. Now, you wouldn't put that big of a circle, but it creates a hole. So a value that's a restriction that cancels out creates a hole. You'll learn about that next year. We don't have to know that for this year. But you do have to know what restrictions are and why they're important in both circumstances. Okay? Let's try another one. Are there any values of, look at this expression over here. Are there any values of x that are not allowed? Okay, well, we can have the numerator can be 0. There's no problem there, okay? So this could equal 0, or this could equal 0. Just like when we were, if this was a quadratic, right, we would use this and it was y equals, right? We would use that to figure out that my x-intercepts are -4 and 5, right? Those are what we actually called the zeros of the quadratic equation. Now we're looking for non-zeros, okay? So we're not really concerned with the numerator. It's not really important to us for the values of x that are allowed. Okay? Where we focus on for a fraction or a rational expression is the denominator. What value of x will make that bottom or that denominator equal to 0? That's called our restriction. And the value of x is going to be a positive 5, because if I go 5 minus 5, that's going to equal 0. Another way that you could do it is the same way that we found our zeros with quadratics when we had something like that. We set this equal to 0 and we set this equal to 0 when we want to know when it was 0. Now we want to know when it's not 0, so we go x minus 5. And we solve, this inequality. So we do it exactly the same way. We move the 5 over to -5 to the other side by adding 5 to both sides. And we get x is not equal to 5. And that's where we get our restrictions from. So it's just like solving an equation, but it's an inequation or an inequality. Okay, so those are my restrictions. What about reducing? It's kind of obvious how this guy reduces, isn't it? We got an x minus 5 in the bottom. See this guy packaged in the bracket? And this guy packaged in the bracket. Now, what we don't do, and what we can't do mathematically, is we can't cross out that x and that x, and that 5 separately. Okay, because a lot of people go, oh, x, 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 and they cancel that out even before they do anything else. Okay, you can't do that. The reason why you can't do that is because of bedmass. This is a division, right? There's division. That's like a division sign, something on the top, something on the bottom. There's the sort of fraction portion. But when you look at this, because it's bracketed, you have to do this operation before you do division. That's brackets. That's the B of bedmass. The D is the D in bedmass, and D and M can be interchangeable, but B is first. We got to do brackets first, so we cannot cancel that and divide them out. We can divide out the entire thing because it's identical top and bottom. And so as a result, expression written in lowest terms? No. Really, x minus 5, x plus 4, all over x minus 5 actually equals to just simply x plus 4. But, of course, x cannot equal 5. Okay? And again, I know that there's nothing left in the denominator, just 1. Okay? But what ends up happening is that tells us that when we graph this function, there's going to be a hole in the function at 5. Okay? So these things that cancel out and disappear in the final result, simplified result, are still holes in that relationship because you can't plug in a value of 5. Okay? Now, when we're reducing and stuff, in considerations, and there's going to be some rules as it gets more and more complicated, because even that one looks complicated. As we get more and more complicated, okay, we're going to have to develop rules. So what I've got here is, for all the techniques we're going to do for this unit, I've got steps to success. If you do these steps, you should be okay in general. Okay? So, what should you do? Well, first thing, this is the question. This is the example that I give you. E.g. is example given. Okay, we have to simplify and state restrictions for this guy. Okay, 4x squared minus 6x over 2x. Okay, and I know you want to start canceling stuff out. You can't. Okay? Remember that when I have a fraction, that's the top and the bottom. They're already bracketed. Okay, so whatever's on the top and whatever's on the bottom, whatever's in the numerator and denominator, they're already bracketed. It looks like this, really, 4x squared minus 6x divided by 2x. Hopefully that's not too dark. The lights just went out. Let me just see if I can get the light sensor to work. Oh, it did. Okay, lights are back on. All right, that's what it is, but in essence, it's bracketed. Okay, and we have to be careful with that. Okay, when we do that, when we deal with these expressions. That's why we're going to learn how to do this step by step, taking baby steps, so life is not crazy. Okay, so step 1, always, this is the first step in any rational expression thing you do, factor fully. Okay, so factor the numerator separate from the denominator, but factor them fully. So if you look at the numerator here, we've got 4x squared minus 6x. Well, we can factor out a common 2x, and then we get x minus 3. Oops, sorry, 2x minus 3. Okay? And here we can't factor anything, so it's just 2x. And so that's the result that we get when we factor fully. Okay? Factoring fully is going to help us with restrictions, but it's also going to help us with seeing what's in common between different things so that we can actually divide stuff out. Here it was nice and factored, right? And so we can see the two of them. But if I wrote this as x squared, minus x minus 20, which is what the numerator is, you wouldn't be able to see that it has an x minus 5 in common in it. You have to factor it first. So I gave it to you in factored form here, but now it's not going to be in factored form. So we do have to factor it so we can see what it has in common. And you can kind of see what it has in common here, doesn't it? Or can't you? You can see the 2x there, the 2x there. They've got something in common that we couldn't see before with the 4x and the negative 6x. 4x squared and negative 6x. Okay, now, before we do anything more, we have to state restrictions, because if we cancel these and they disappear, we're going to be missing a hole in the function, and we can't miss a hole in that function. So what we have to do is we have to state restrictions before we do any dividing. And I know you want to divide these two guys. It's like here, very satisfying. God, they're gone. Now it's so simple, x plus 4. But you don't want to divide yet. Second step is going to be state restrictions. So what are the restrictions? Well, again, the restrictions are focusing on the denominator. I've bolded it right there for you. So I set the denominator not equal to 0, and then I isolate for x. In this case, x can't be 0, okay, because 2 times 0 is going to give me 0 for the denominator. Okay, denominator cannot equal 0. So now we have our restrictions. X cannot equal 0, and it's more simplified. The next step is cancel or divide out terms or expressions found in the numerator with what is found in the denominator. Now, the rule for this is like cancels with like. And what that means is a monomial, like 2x, can cancel with a monomial 2x. But this monomial 2x cannot cancel with, so this 2x here can't cancel with this 2x. This guy can't cancel with this guy. This is a monomial, and this is a binomial in the bracket. Binomials can only cancel with other binomials that look exactly the same. And even trinomials can only cancel with other trinomials that look exactly the same. Okay, so here we have a monomial. Okay, and that monomial, you'll see monomial, numerator, denominator, they can divide out. And in the end, you'll see I've got this little crossy function here. Okay, and so as a result, what's left? Well, it is over 1 in the denominator, but it really turns into 2x minus 3. And our last step when we do this, okay, before the step 3 is cancel or divide out terms, step 4, restate and restrict. It's just a closing statement. This says that what I started with and what I ended up with are the same. So therefore, the numerator, the original question is equal to really 2x minus 3. However, we do have a restriction where x cannot equal 0. So that's restate, and restrict, restrictions, R and R. Okay? And so that's how the process works. So let's try some of these. And we only have about 10 minutes left in this lesson because I have a meeting that I have to go to, and more importantly, the video, I don't want to be too long anyway. So let's go through as many as we can. The factoring step will be saved for the first 4 so we can focus on restrictions and canceling. So for this one, first step, factor fully. There's no factoring to be done. It's a monomial over a monomial. The monomial can't have anything in common with anything else because it's only one of them. Okay, so you can't factor even if you wanted to. Second step, determine the restrictions. So, in this case, my x squared cannot equal 0, or x cannot equal 0. My y cannot equal 0. So all of these guys, they're in the monomial, they cannot equal 0. You can't have a 0 there. You can't have a 0 there. You can have zeros in the numerator. I don't care about that. That's a coincidence. It's really about what's in the denominator. Okay, so that's our second step. So we've got our 2 restrictions. You can, I don't know, circle them or something, or maybe write them small on a scrap piece of paper. But you're going to want to communicate that idea somewhere. And then step 3 is cancel or divide out terms or expressions found in the numerator. Like cancels like. I've got a monomial on the top, monomial in the bottom or monomial in the numerator and monomial in the denominator, so I divide it out. Numbers affect numbers, so I can cancel the negative 10 and the 25 and be left with negative 2 and then a 5 in the bottom. And so a 5 in the bottom, so they cancel out. You know, it sort of reduces down, 10 over 25 reduces down to 2 over 5. Okay, the x cubed and the x squared, I cancel those out. And really what I do is I subtract the exponents. So the greater exponent is x on the top. So we have more on the top than on the bottom. So this cancels out entirely, and I'm left with 1, x to the power of 1. And then for y squared, same idea. Y on the bottom cancels with the squared, and we're left with y to the 1. Okay, it's a little bit of an ugly look to it because we're building it piece by piece. And I guess I should probably put the 5 maybe here. But there's my final expression. Now, the only thing I really have left to do is restate and restrict. So therefore, negative 10x cubed y squared all over 25x squared y, a little bit ugly, is equal to negative 2xy over 5, and then x and y cannot equal 0. Oops. Cannot equal 0. There's my inequality. Okay, so there's that guy. I kind of put it in a little box there so it separates it from the other one. All right, that's how we do that one. All right, another example. Okay, we always learn from these examples, right? First step, factor. Well, what you'll notice is that the numerator's factor, the denominator you can't factor. There's nothing in common between the two of them. Second step, state restrictions. So what are my restrictions here? Well, you can go x minus 5 cannot equal 0, and x cannot equal 5, but I think a lot of people can just look at it and realize that that's a 5, especially from last year when you were doing quadratics. You got pretty good at being able to see zeros for quadratic equations. All right, so let's go further because I do want to get through as many of these as we can. All right, so the third step is, after we stated restrictions, is we cancel. Like cancels like. Well, here you'll see an x minus 5 and an x minus 5. So the binomial cancels with the binomial, and I'm left with an x. So therefore, x times x minus 5 all over x minus 5. I'm writing this a little fast so that we have some time, so try to make sure that you write it a little bit neater next time, is equal to x, and then you say x cannot equal 5. That's where the hole is for the equation. Okay, and that's sort of your closing statement there. Okay, same idea, closing statement there. All right, this one's a little bit more complicated. Okay, here again, it's already factored, so we don't have to do step number 1, but we will do them down here. We could also see that the restrictions, a little bit more elaborate. Maybe I'll do the restrictions up here. So for this one, we'll say, well, 2x cannot equal 0. Boop. X is equal to 0. Okay, divide both sides by 2, and you know that x cannot equal 0. Or y minus 3 cannot equal 0. Or y cannot equal, bring the negative 3 over, add by adding 3, and it becomes y cannot equal 3 and x cannot equal 0. Okay, as far as canceling is concerned, I cannot cancel those two. They have to be exactly the same to cancel. However, monomial and monomial can cancel. Binomial and binomial can cancel if they're exactly the same. These ones have some things in common. So my 10 and my 2 can cancel to 5 in the numerator, and I guess 1 on the denominator, but I won't include a 1. The x, so this cancels to 5. The x's cancel out and sort of disappear. Okay, I'm left with a y, and then I'm left with y minus 2 all over y minus 3. Nothing too crazy in that scenario. Okay, another example here. Restate and restick. You know what I'm going to do to save time so I can get to more examples? I'll just go R and R. Therefore, this guy equals this guy, and those are my restrictions. Okay, so do as I say, or do as I say, do R and R's, not as I do in this particular example here. And this one's a little tricky because you notice you can't factor it. For my restrictions, not too difficult. 4 minus a cannot equal 0. You can move the a over here, so a cannot equal 4. Or you just say 4 minus 4, a can't be 4. Okay, that's no problem. The restrictions are easy. There's no factoring to do. But what you'll notice is that they're different from each other. Okay, and so they don't cancel out. But sometimes, if you're clever, you can factor out a 1 or a negative 1. Okay, maybe I should do this in 2 steps. So if I factor out that negative 1, that becomes a negative 4 plus an a, and if I rearrange those guys, I go a minus 4, and then I go negative 1. And then I go negative 4 goes over here, a goes over here, I got a positive a minus a 4, and then I'm like, oh, it cancels out, and it ends up being 1 over negative 1 or negative 1. And so that's what it simplifies to. Okay, it's a little bit of a trick. Okay, and then don't forget your R and R. Okay? Now, I may have to break this video into 2 pieces, and I think that's what I'm going to do because I do want to get to more of these examples for you, but I do have a meeting that I have to go to. Okay, so I'm gonna go to that in about 3 minutes. I'll be able to get another 1 or 2 behind my belt or under my belt. Okay, so first one, I want to factor. What does the numerator have in common? Okay, there's a 7 and an x in common. Okay, that goes into 7 goes into 35 as well. And then 7x squared divided by 7x is going to be x. Negative 35 divided by 7 is negative 5. X divided by x divides out. In the denominator, you'll see that there's a 2 in common between those two. So you factor out the common 2. 2x divided by 2 is x. Negative 10 divided by 2 is negative 5. Okay? Factor is your first step. Second step is your restrictions. X cannot equal, in this case, 5. The 2, there's no variable with the 2, so that's fine. Okay? And then we reduce. X minus 5 and x minus 5, identical binomials, they will reduce, and I'm left with 7x over 2. And then, of course, don't forget R and R. So therefore, this is equal to 7x over 2, and x cannot equal 5. Oh, I got enough time to maybe get the next one in here. I'm going to factor a little bit quickly. What multiplies to give me negative 8 and adds to give me negative 2 is x minus 4, x plus 2. And then in the denominator here, I've got a common 3x plus 2. Okay, first step is factor, second step is restrictions. In this case, x cannot equal negative 2. You see the negative 2 that's in there. Negative 2 plus 2 makes it 0. And then, of course, we can cancel. And the canceling we can do is with the x plus 2 and the x plus 2. Okay, and that leaves us with an x minus 4 all over 3. Those binomials have to be exactly the same for them to cancel out. And then don't forget, do as I say, not as I do. Reduce and restrict. But that's really the final answer there. I could probably get one more in, and they'll start the meeting a little bit late. Yeah, I may have to go. I'll join the meeting late. That's fine. Okay, so what multiplies here to 2 times negative 12 negative 24?
That we're going to have a...
Okay, so that's my time. I got to go. All right, I'll come back and finish those.